Hello, my name is Chris Dunn, and I'm the director of the Hydrologic Engineering Center, or otherwise known as HEC. This is the second part of the four-part series where we introduce Engineer Regulation 1105-2-101 and provide background on policy and regulations for risk assessments. Specifically, in this presentation, we're going to introduce you to key sources of uncertainty, some specific guidance, and how it applies to smart planning. The objectives for this presentation or this series and what will be introduced specifically throughout this presentation are listed here. In the previous presentation, we provided an introduction to ER 1105-2-101, and we explained the risk framework. In this presentation, we will define key risk assessment terms and sources of uncertainties. We will define NED in another presentation and understand economic and performance reporting requirements and communication and other considerations, and identify impediments to risk assessments in subsequent presentations. So before we go on, let's talk a little bit about some definitions that you will use throughout your risk analysis. First, risk is the likelihood and severity of an adverse outcome. That's its most generic definition. Really, in a flood risk management study, it's the probability of an area will be flooded, resulting in undesirable consequences. Why is undesirable consequences important? Because you might have an environmental area where you want the floodplain to get inundated at a certain frequency. That's not an undesirable consequence, so it has less risk. So really, for a flood risk management study, when we define risk, we're talking about the probability that an area will be flooded, resulting in undesirable consequences. Uncertainty. That is the result of imperfect knowledge of parameters and functions used to describe the hydraulic, hydrologic, geotechnical, economic, and life loss aspects of a project plan. We will talk about each one of these disciplines and their uncertainties later in this presentation. Risk assessment, as we defined in the previous presentation, is an approach to the evaluation and decision-making that explicitly and to the extent practical, analytically incorporates considerations of risk and uncertainty in a flood risk management study. Some other definitions: annual exceedance probability, or AEP. Let me just read this and then we'll go back and talk about what it really means. Annual exceedance probability, or AEP, is the probability that a certain threshold may be exceeded at a location in a given year, considering the full range of possible values and, if appropriate, incorporation of project performance. So what does that really mean? What it really means is, what's the likelihood of you getting wet where you're standing? So if you're on the exterior side of the levee in the floodplain, your likelihood of getting flooded is much greater than if you were on the interior or the dry side of the levee. So if you're standing on top of the levee, your likelihood of getting wet in a given year should be considerably less than if you were on the exterior side of the levee. So you define that threshold. That threshold is, okay, am I on the interior, exterior, on top of the levee? And then it's exceeded at a given location and in a given year, considering the full range of possible values. Full range of possible values means what are the least likely events to the most likely events. And you consider that full range of possibility of all those things in a given year, and you incorporate the probability that your project will perform as you expect. So it's the likelihood of you getting wet in a given location in a given year, considering the full range of floods and with the incorporation of project performance. Residual risk is the flood risk that remains if a proposed flood risk management project is implemented. You will still have risk even though you build a flood risk management project. So residual risk includes the consequences of capacity exceedance as well as project performance. And you will need to define what residual risk is if you build that project. Some potential key sources of uncertainty in hydrologic uncertainty. So in ER 1105-2-101, the key sources of uncertainties are identified per discipline. So hydrologic uncertainty, record lengths. We talked about that in the previous presentation. But if you have a short record length, you have high uncertainty. A long record length, less uncertainty. But in addition to that, a lot of times your projects are not located where you have gauged information. So therefore, you have to translate your gauged information from the gauge to the project itself, which introduces additional uncertainty. Then there's the estimation of parameters in a rainfall runoff computations. So routing parameters, precip parameters, whether it's rain or snowfall, temperature, infiltration rates, base flow, are all to some degree uncertain. And therefore, you have to reflect that uncertainty in your computations. Effectiveness of flood flow regulation measures, such as reservoirs. Do you know that that reservoir will operate as you expect? You may or may not know. So therefore, there's some uncertainty even with flood flow regulations. Potential sources of hydraulic uncertainty, conveyance roughness, whether the managed roughness value is 035, 045, 055. At HEC, we did a poll where we surveyed students in our classes. We showed them pictures of various stream channels and asked them what the managed roughness values would be for those particular stream channels. And what we saw was fairly wide array of answers for those various stream crossings. And because of that, you can tell that there's a lot of uncertainty associated with your selection of a conveyance roughness factor or managed N value. Cross-section geometry, whether you have good bathymetry or you're using LiDAR information, you're using a DEM to pull off your geometry, all are factors in the amount of uncertainty that you have with respect to your cross-section geometry. Debris accumulation, ice effects, both influence the water surface elevations, and so can adjust your water surface elevations, and therefore uncertainty is a factor. Sediment transport, flow regime, whether you're a sinuous channel, a braided channel, you have an alluvial fan, bed form changes, all are factors in what your water surface elevation will be, and therefore there's all uncertainty in each one of those factors. Geotechnical uncertainty, physical characteristics and construction quality of the levees. Do we know those with certainty? Generally, we don't. There's just too much history in those levees to know exactly how they were constructed, when they were constructed. There's also difficulties related to locating and installing temporary barriers, in a timely manner. And then information from borings representing the length of the levee. Typically, we don't have enough time. We don't have enough money to develop or get borings everywhere we want them. So therefore, we let a few borings represent the entire length of the levee. And those borings may or may not actually represent the length of the levee. And so therefore, we don't necessarily know the structural integrity of that particular levee. Economic uncertainty, depth damage curves. They may be generic depth damage curves and do not represent many of the structures in that particular location. Structure values. If we do a survey, we may not know all the structure values in that particular neighborhood. We may know some of the structure values in that particular neighborhood. Content values. Likely we don't know the values of the contents in the various structures that we have surveyed. And we make assumptions about the content values in the structures we haven't surveyed. Structure first floor elevations. Obviously, we don't know those with precise precision. Structure types. We make assumptions about the structure types. Flood warning times can adjust and can change our economic outcomes, as well as flood evacuation effectiveness. We give a flood evacuation warning, but do people heed that warning? And with flood warning times, whether we give people 12 hours, 24 hours, 48 hours of lead time will make a difference in what they're able to save and what they're able to move out of the floodplain. And this doesn't account for agricultural information because ag damages is impacted by the season of the year that the flood occurs, whether your crops have reached maturity, whether they have been planted or not, those types of things. So there's economic uncertainty with ag as well. Key sources of uncertainty and life loss. The number of egress routes. How many routes are there for people to get out of a particular neighborhood that's being flooded? Time of day, whether it's nighttime and you're asleep versus daytime and you're at your place of business, whether your kids are at school or your kids are at home. Distance to dry land is a big factor, whether you can walk, drive to that dry land. Water temperature, whether the temperature is 40 degrees or the temperature is 60 degrees, may determine how long you can survive in that water temperature. Number of multi-storied structures to get out of the floodwaters, the demographics. How many, what population or percentage of the population is over 65? Clearly, people over 65 tend to have mobility issues more than people younger than 65. So demographics is an impact. And the existence and adherence to an emergency action plan are all key factors for the uncertainty of your life loss computations. So some specific guidance. All flood risk management studies will adopt the risk framework. And if you remember from the last presentation, that means a risk assessment, risk management, risk communication. The risk framework approach and results should be documented in the principal decision document. Ultimately, that would be the chief's report. The types of documents involved are all the things that we talked about in the previous presentation: feasibility reports, project modification, impact reports, so on and so forth down the line. So again, pretty much anything you're working on will require a risk assessment. Some more specific guidance. The project management plan, or PMP, will describe the methods to be used to quantify the uncertainties of key variables. The key is key variables, not all variables, parameters and components, and the approach to combining these uncertainties into higher level measures of overall economic and engineering performance. So in the PMP, you should define your key variables of uncertainty and then how those key variables are going to impact your analysis. In cases where a general reevaluation report is proposed and standard freeboard assumptions or other engineering standards were used, which are critical to sizing or performance of the project features, a reformulation of the project using a risk assessment must be used. So this is happening less and less as we use more and more risk analysis and risk assessment. But it used to be that freeboard was this term that we used to capture all of our uncertainty. So if, for example, on a FEMA floodplain analysis, it used to say that you needed 3 feet of freeboard. Well, why 3 feet? Why not 4 feet? Why not 2 feet? The reality is that they didn't know, and they used freeboard as a safety factor for all the uncertainty that might be incorporated in the hydrologic and hydraulic analysis. So we do not use freeboard anymore. We use a risk analysis to properly define the amount of uncertainty that we can expect from those various parameters. Smart planning, the ultimate goal is a comprehensive approach to in which the values of all key variables, and again, key variables, parameters and components of flood risk management studies are subject to a probabilistic analysis. Not all variables are critical to project justification. So again, in your PMP, you're going to define those key variables. So in progressing towards the ultimate goal, the risk assessment and study effort should concentrate on the uncertainties of the variables having a significant impact on study conclusions and recommendations. Not all of the uncertainties, but the ones that have a significant impact. And the level of detail to make decisions will grow over the course of the study as you move to fewer alternatives. So as you go from having just a few alternatives, many alternatives, to having just a few alternatives, your study detail will continue to increase and your analysis of uncertainty will continue to get more and more detailed. So we've completed the second of 4 presentations in this series. In this presentation, we identified key sources of uncertainty, discussed some specific guidance, and how uncertainty is used in smart planning. Now would be a great time to capture any questions you have on this session, and we can discuss them later in one of our discussion sessions. Thank you, and I look forward to talking to you in our next presentation.